Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam exam and other exams related to physical science. Okay, so this is the lecture number 14, in which I'm going to discuss rectangular potential barrier and Dirac delta potential. Okay, these two are very important, and we'll solve some questions related to that as well. Okay, before starting the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes which are going to help you to crack the examinations related to physical science. Okay, so I'm going to start now. So I'll start with potential barrier first, rectangular potential barrier. Okay, this is lecture number 14. Okay, so rectangular potential barrier. Okay, meanwhile just let me check, am I audible or not? Rectangular potential barrier. Okay, yes, I'm audible. So I'll start now. Okay, okay, so I will define a rectangular potential first. Okay, rectangular potential barrier. Okay, so this is Vx, that is 0. Okay, value of Vx is that is 0 if x is less than 0. I will draw the figure, then it will be it will clear your doubt. Okay, and second is value of Vx is V naught when uh, x is between 0 to a. Okay, and again Vx is value is 0 when x is greater than a. Okay, so this is the potential. Okay, for rectangular barrier. Okay, it is 0 if x less equal to if it is 0 if x less equal to 0. Okay, and it is V naught if x is between 0 to a, and it is again 0 if x greater equal to a. Okay, so this is the potential of rectangular barrier. Now I will make a figure. Okay, so just let me make a figure first. Okay, I'm going to make it again. Width of rectangular barrier is A and height is V naught. Okay, let me draw it first, then it will clear your doubt. Okay, so this is the rectangular barrier. Okay, width A and height is V naught. Okay, as defined here, and this is the energy E, which is less than V naught. Okay, less than V naught. We can clearly see in the figure. Okay, so the wave of particle, right? That is wave comes like this from first region, and then this goes like this, and then again this goes like this. Okay, so this is the region first, this is region second, and this is region third. Okay, and this is the potential barrier which we have defined. Okay, so here you can see when it is in region 1. Okay, so you can see it's oscillatory wave. Okay, moving towards positive x-axis direction. Okay, here you can see the energy, right? Energy of the wave is less than V naught, the width of the potential barrier, right? So if classically it cannot penetrate this barrier, but quantum mechanically it will penetrate. So there is a probability of finding the particle inside this barrier, right? So this will be the wave, and then again after after this barrier, right, again it will move with the same energy E, right, in region 3. Okay, so for that we'll write Schrodinger equations and the wave functions. Okay, Schrodinger time dependent equation, we know that is time independent Schrodinger equation, right? That is del square psi upon del x square plus 2m upon h cut square E minus V naught psi equal to 0. So this is the Schrodinger equation, right? So the wave function of this is going to be, for region 1, the wave function, that is psi 1, is going to be that is a e to the power iota kx plus b e to the power minus iota kx. Okay, this is the wave function for the first region, right? This I have already explained in detail how we get the wave function from the Schrodinger wave equation in my previous lectures. Okay, so you can watch those lectures. Okay, So this is the one. Now for region second, wave function psi2 is going to be for this, right, for this one. Here you can see there is probability of penetrating that particle inside this potential barrier, right? So this is going to be, and this wave will not be oscillatory, okay, it will be non-oscillatory. So it is going to be, and I have explained what is oscillatory, non-oscillatory, what is the wave function associated with in my previous lecture. You can check it, okay. So this is going to be psi2 is going to be c e to the power alpha x plus d e to the power minus alpha x. So this is the wave function, okay. Here where value of k is root 2 me upon h cut square, okay, and here the value of alpha is root 2 m v naught minus e upon h cut square, okay. This is for the second region, okay. This will be non-oscillatory, means they wouldn't so here you will not get any iota term, okay, in the wave function, okay. Now for region third, for region third, psi3 is going to be e to the power iota kx plus d e to the power minus iota kx, okay. Here you can see because after penetrating this, when the wave will be in second region, right, the wavelength of this particle, the wavelength of this wave and wavelength of this wave, or wave vector of this wave, will be the same, okay, because there is no potential barrier, okay. So this is one, and here we can see okay, so this is f, guys, f, right. Here we can see in this region we can see there is a wave coming, right, and then there is wave, this is incident wave, and then this is also reflecting because of potential barrier. That's why there are two terms. This shows deflection wave function, this is incident wave function. Here you can see this is going, right, there are finite probability of going, so there is chances of deflection as well as incident, right. So that's why there are two waves, this one. Similarly for region third, we can see there is no reflection. Why? Because there is no barrier, right. So this wave is just transmitting, so that's why in that case this wave function associated with reflection will be 0, means that implies f equal to 0, okay, and that means implies f e to the power iota kx, this value is going to be 0. So for psi3 for region third is going to be, the wave function is going to be e to the power I kx, okay, this one. Next, so these are the wave functions, okay. Now I have already explained in my previous lecture how to find what is reflection coefficient, what is transmission coefficient, how to find reflection and transmission coefficient, right. So in my previous lecture that is potential step I have explained, okay. So now we'll write the reflection coefficient for this wave, okay. This is a condition, guys, okay. So there is a condition is here, the condition is, this is the case 1, okay, case 1, and this is condition is v naught greater equal to e. You can see from the figure clearly e is less than v naught, okay. So this is the case, and then reflection coefficient is going to be 1 plus 4e v naught minus e upon v naught square sine hyperbolic square ka whole to inverse or whole to the power minus 1. Okay, so 1 plus 4e and v naught minus e upon v naught square sine sine hyperbolic square k to the inverse, right? And the transmission coefficient is going to be 1 plus v naught square sine hyperbolic square sine hyperbolic square ka upon 4e v naught minus e whole to the inverse. Okay, so if you know that reflection coefficient, you can easily find out transmission coefficient. Okay, how does it trick? Like, so here you can see this is the reflection coefficient, right? For getting transmission coefficient, what you need to do is you need to write same reflection coefficient and then you need to exchange the position of numerator and denominator, right? So this is going to be 1 plus v naught square sine square hyperbolic ka upon 4e v naught minus e inverse. Okay, so these are the reflection and transmission coefficient for the rectangular potential barrier. Okay, well, now we will study case second. Okay, case second is when let me check my internet working fine. Yeah, it's working fine. I'm just checking am I audible or not. Okay guys, on, yes, I'm audible. Okay, so now case second. In this second case, E, that is energy, is greater than V naught. Okay, so I will make a figure for this as well, right? So it will be more clearer to you then. Okay, so let me draw the figure. Okay, I'm just drawing the figure. This is the potential barrier. Our width is A. Okay, here. Okay, so this is the case second. Let me just write. This is 0. This is the width of the rectangular barrier, and this is the height of the rectangular barrier. Okay, like this. and here we can clearly see in the figure that energy is greater than V naught. Okay, so this is region first, and this is region second, and this is region third. Okay, so now in first region wave is coming like this. Okay, this is oscillatory wave. Okay, and in the because in it will go in region second, obviously it will go. Okay, because we can see energy of the wave is greater than the potential barrier. Okay, but here we will see, let me just draw this again, because it's a barrier, right? So wavelength of the wave will get increased. Okay, because it is in higher energy, the wave is in higher energy barrier. Okay, so in potential barrier, right? If wavelength of this wave is lambda, then it is lambda dash, and clearly lambda dash is greater than lambda. Okay, lambda dash is greater than lambda, or we can say if the wave vector for this is k and if this is k dash, then clearly k is greater than k dash, because we know lambda equal to 2 pi by k, or k equal to 2 pi by lambda. Okay, so here again in this region, the region in this in region third, the wave vector is going to be k, and wavelength of wave is going to be lambda, right? Because there is no barrier, or there is no potential, right, in the region third. Now I will write Schrodinger equation for it. Okay, so I'm going to write Schrodinger equation. Okay, this is the case if E is greater than V naught. Okay, this is this one case. Okay, so now okay, so now we know the Schrodinger time dependent equation, right? So that is time dependent Schrodinger equation, that is d square psi upon dx square plus 2m h cut square e minus v naught psi is going to be 0. So for region 1, that for region this, okay, the wave function is going to be, we know how to do it, right? So you can check my previous lecture. Okay, so psi 1 is going to be, that is a e to the power iota kx plus b e to the power minus iota kx. Okay, from here, right, this is going to be like this. From there, this is a barrier, right? So it is also transmitting, so that's reflecting, so that's why this is the wave function. And for region 2, psi 2 is going to be, for region 2, psi t is going to be c e to the power iota k dash x, okay, plus d e to the power minus iota k dash x, because the wavelength gets increased in the potential barrier, right? Because that is in potential. Okay, so wavelength of the wave is increased, and the wave vector for that is k dash. Okay, and here the value of k dash is going to be root 2m e minus v naught upon h cut square. Okay, and value of k we know, right? K is root 2me upon h cut square. Here e is greater than v naught. Okay, for region third, the wave function psi 3 is going to be e to the power minus iota kx, there is no barrier, right? So the wave vector will remain same. So and f e to the power minus iota kx. Okay, and in this region, because this region you can see in the region third there is no transmission, right? Because there is no barrier. So so it means this f is going to be 0. There is no transmission. Okay, so this means since there is no transmission in region third, this implies f equal to 0. That implies f e to the power minus iota kx equal to 0. So psi 3, the wave function in region third is going to be simple, that is e to the power iota kx. Okay, so this is the psi 3. Okay, now we'll find r, the reflection coefficient, and the reflection coefficient is going to be here 1 plus 4e into e minus v naught upon v naught square sine square ka. Okay, sine square ka whole to the power minus 1. Okay, and transmission coefficient is going to be 1 plus, we'll just exchange the position of numerator and denominator from here. Okay, so this is going to be v naught square sine square ka upon 4e e minus v naught whole to the power minus 1. Okay, 1 plus v naught square sine square ka upon 4e e minus v naught. So this is reflection coefficient and transmission coefficient when e greater equal to v naught. Okay, so there is one case which also we are going to study also. Okay, and that is if one case we are going to study for this, if E tends to V naught. Okay, if E tends to V naught, if that is the case. Okay, if E tends to V naught, that implies K dash A equal to is small. Okay, small, and that means K dash tends to 0. Okay, that means sine K dash A almost equal to K dash A almost equal to K. Okay, right? So we will write this. So then if in that case R is going to be, reflection coefficient is going to be 1 plus 4e, will put the value 4e e minus v naught upon v naught square sine square k is going to be like k whole square. Okay, and inverse. Right? So now we will put the value, that is k dash. Okay, we can write almost equal to sine k. Okay, so k dash, so we'll put the value, and value of k dash we know, right? 1 plus 4e e minus v naught upon v naught square, and k dash value is root, okay, it's k dash square, right? So this is going to be 2m e E minus V naught upon H cut square into A whole inverse, okay, A square, okay. So then the value of R is going to be 1 plus 2H cut square upon 2H cut square upon M V naught A square, okay, because here H will go up, 2 will cancel 4 by 2, okay, and then E is almost equal to V naught, right? So it will get cancelled. So after simplifying, this is the value of reflection coefficient when E tends to V naught, okay, and transmission coefficient is going to be equal to the inverse, okay, and transmission coefficient is going to be 1 plus, we'll just exchange the position of numerator and denominator, so it is going to be M V naught A square upon 2H cut square whole inverse, okay. So 1 plus M V naught A square upon 2H cut square inverse, and R is 1 plus 2H cut square upon M V naught A square, okay. So these are the reflection coefficient and transmission coefficient when R equal to, when V tends to V naught, okay, E tends to V naught, okay. Well, so this is about reflection coefficient and transmission coefficient for the rectangular barrier, okay. Now we are going to start Dirac delta potential, okay. Next topic is Dirac delta potential. Dirac delta potential, okay, very important, which we are going to discuss now, okay. Okay, so first I will define Dirac delta, okay. So Dirac delta we know, right, this one. I have also taught Dirac delta, a complete Dirac delta function in my mathematical physics lecture, okay. So we know like this, okay. Like this, right? This is very narrow, guys, okay, very narrow. This is, okay, so it's x equal to 0, okay, this is delta x, okay, this is not like this, okay, this is very narrow like this, okay. I'm just showing. So this is we know the Dirac delta, right? Dirac delta x value is infinite at x equal to 0. At x equal to 0, the value of Dirac delta is infinite and 0 otherwise, okay, 0 elsewhere. This is Dirac delta function, okay. This is very narrow spike, okay, and this is very high, tends to infinity, okay. So delta x equal to infinity when x equal to 0, or delta x equal to 0 elsewhere otherwise, okay. This is the Dirac delta function we know, right? This is how this Dirac delta function is defined, okay. Well, so now I will define Dirac delta potential, okay. So like we can make like this as well, because very narrow spike. This is like this, okay, like this, x equal to 0, okay, x equal to 0, and then delta x equal to infinite at x equal to 0, elsewhere it's 0, okay. So this is actually the graph, okay. So this is very narrow, and this height is tends to infinity, very high, okay. Well, now I will define this Dirac delta potential, okay. So Dirac delta potential, for that I am going to make a figure, So this is like this. This is straight line, guys. Okay, and this is straight line, and this is also straight line. This is 0, and this is tends to infinite, and this is minus infinite. Okay, and this is like this, and this is like this. Okay, this is the Dirac data. This is region first, and this is region second. Okay, and this is I, and this is the energy. Okay, and the energy is equal to minus mod E. Okay, and Dirac delta potential, that is Vx, is defined as Vx equal to minus V naught delta x. Okay, so this is the Dirac delta potential, guys. Vx is minus V naught in 1D minus V naught delta x. Okay, and this is the region first, this is region second. Okay, this is the energy which is value of E is minus mod E for bound state, because for bound, this is the energy for bound state. Okay, bound state, energy for bound state. Okay, this is how we define the Dirac delta potential. Okay, this is the value and this is the diagram. Okay, and this is for bound state. Okay, this is region first and this is region second. Okay, this is between minus infinity to 0, and this is between 0 to plus infinity. Okay, well, so now I will write the Schrödinger equation for Dirac delta potential. Okay, so it is we know that is Schrödinger time independent Schrödinger equation, right? So this is d square psi upon dx square plus 2m upon h cut square E minus Vx psi equal to 0. This is the Schrödinger time dependent equation. Now we will write the value of Dirac delta function, Dirac delta potential, which we have defined. Okay, which is defined. So this is going to be d square psi upon dx square plus 2m upon h cut square E plus V, value is this minus minus plus. Okay, so this is plus V naught delta x plus V naught delta x, okay, into psi equal to 0. Now we know Dirac delta this definition, right? If delta x at x equal to 0, delta x is infinite, elsewhere it is 0. Okay, otherwise it's 0. Okay, so we will use here. So here for bound, okay, for when x not equal to 0, then delta x is going to be 0, right? From this definition, if x not equal to 0, then elsewhere the delta x is 0. Okay, from this condition, so what is going to be? It means delta x, this is going to be 0, right? For x not equal to 0, it means this equation is going to be reduced as d square psi upon dx square plus 2me upon h cut square psi equal to 0. Okay, now for bound state, for bound state okay, for bound state we know energy E is minus mod E, right? This is for bound state, so we'll put the value here. So it is going to be we'll replace E by minus mod E, so it is going to be del square psi upon del x square, okay, plus 2m upon h cut square minus mod e, okay, psi equal to 0. Okay, so this is going to be d squared psi upon dx square minus k squared psi equal to 0, where k, value of k square is going to be root 2me upon h cut square, okay, or 2m mod e upon h cut square. Okay, this is the value. Now what we are going to do, we'll solve it. Okay, and after solving we will get the Schrodinger equation, that is, sorry, the wave function, and the wave function is psi x is going to be equal to that is a e to the power I kx plus b e to the power minus iota kx. Okay, so this is the wave function. Okay, now so we'll define for region 1 and region 2. Okay, so this is for region 1 and region 2. Okay, so region 1 and region 2, so we can see here this is region 1 minus infinity to plus 0, and region 2 is 0 to infinity. Okay, so for that reason, right, the wave function is going to be, so for region 1 x lies between minus infinity to 0, right, so it means psi minus infinity is going to be 0, right. This implies we'll put the value, right, this we'll put value, this one, so minus infinity in this psi. So after putting, it is giving b equal to 0. Okay, so psi 1 equal to, this is for region 1. Okay, right, psi 1. Okay, psi 1 equal, I'll solve it also. That will be better. Okay, I'm going to solve it. So I'll put the value. So psi infinity is going to be, that is psi a e to the power k into x value is minus infinity plus b e to the power minus k into minus infinity equal to 0. I have put value this in this, right, x equal to minus infinity. I have put this value in equation 1. Okay, so I've put it. So it means this value is going to be a e to the power minus infinity plus b e to the power minus plus infinity. Okay, that is infinity equal to 0. So we can see this value is 0. Okay, and this value e to the power infinity cannot be 0, right. This implies b equal to 0. Okay, b equal to 0. This is how we've got b equal to 0. Okay, so now it means the psi 1, the wave function for region 1 is going to be, since b equal to 0 here, right, so from equation 1 it is going to be a e to the power iota kx. Okay, now for region 2, which is this, right, from 0 to infinity, 0 to x is between 0 to infinity. So we'll write x infinity, that value is going to be 0. Again we'll put the value. So a e to the power in this equation 1. Okay, equation 1, this is e to the power iota k, e to the power iota k, this is iota as well here, iota. Okay, e to the power iota k, and this is infinite plus b e to the power minus iota k into infinite equal to 0. So this value is a e to the power infinity plus b e to the power minus infinity. This value is going to be 0, right, because e to the power minus infinity is 0. and here you can say e to the power minus infinity. E to the power infinity cannot be 0, right? So it means a is 0. So this implies a is 0. So wave function psi 2 is going to be for region 2. This is going to be b. This is b e to the power minus kx. Here we have done some mistake. Okay, what mistake? So this is minus, right? So this is going to be, this is just wave function is a e to the power kx, and this is b e to the power minus kx. So there is no iota term, right? Okay, b e to the power minus kx. Okay, so here this is going to be, I will not be there. Okay, okay, so iota is not there, because if we solve it, this is going to give value is the auxiliary equation going to give value x equal to plus minus 1. Okay, sorry, this is plus minus k value of x going to be, okay, for value of m, sorry, for auxiliary equation. So this is iota iota term is not here. Okay, so this is minus k and minus k. So these are the values. Okay, for region 1 it's a e to the power kx, for region 2 it is b e to the power minus kx. Okay, so this is the wave function for region 1 and region 2, for this region and this region. Okay, now next what we are going to do is, we will normalize this. Okay, in the same way we'll be divided into two parts by drawing a line. Okay, so here so we'll normalize it. Okay, so value of this is this a. Okay, so now normalize. So normalizing, we know, right? Minus infinity to plus infinity, right? Sorry, minus infinity for region 1, minus infinity to 0, and psi star psi equal to 1, right? And this is psi, and psi star going to be same, because this is real function, right? So it is going to be mod a square minus infinity to plus infinity, so e to the power kx into e to the power kx, right? So this is going to be e to the power 2kx equal to 2kx dx equal to 1. Okay, 2kx dx equal to 1, right? So again we'll write it. So it is going to be mod a square, and we'll put value here. So this is e to the power 2kx upon 2k to the power minus infinity to 0 equal to 1, right? And if that implies value of a is going to be root 2k. Okay, similarly here we'll normalize the second wave function, that is wave function in region 2, that is 0 to infinity. Okay, and the wave function is this. So this is going to be e to the power minus k, e to the power minus kx, e to the power minus kx, right? So psi star psi, so e to the power minus 2kx, and this is mod b square will outside, dx equal to 1. So we'll again simplify it, mod b square, and this is e to the power minus 2kx upon minus 2k 0 to infinity equal to 1, and we put the value. So mod b is going to be, so mod b square is going to be 2k. Okay, 2k, and then this implies value of b is going to be 2k. Okay, right? So here we can write in next phase. So psi1 is, so therefore normalized wave function for region 1 is root 2k e to the power kx, and psi2 is going to be root 2k e to the power minus kx. Okay, so these are the wave functions, okay, uh, for region first and region second. Okay, now we can write the complete wave function for Dirac delta function. Okay, that implies complete wave function for Dirac complete wave function for Dirac delta function. Complete wave function for Dirac delta function. Dirac delta potential is going to be Dirac delta potential. Okay, is going to be, we can write that psi equal to root k e to the power minus k mod x. Okay, so we can write like that. So this is the we can write c, not root k, it is c, combined wave function. We can write this. Okay, so complete wave function for Dirac delta potential. Okay, so this is psi equal to e to the power, we can define like this. Okay, e to the power, it is going to be like the e to the power minus k mod x. Okay, mod x c e to the power minus k mod x. Okay, right. So now we'll normalize it. Okay, so normalization we know, right? So this is the psi. So normalization is psi star psi dx is going to be 1. Okay, this is 1. Okay, 1, and this is psi, and implies psi star is going to be c, same, c e to the power minus mod kx, e to the power minus k mod x. Okay, right. So we'll normalize it now. It is going to be integration. Okay, integration minus infinity to plus infinity, and this is mod c square. Okay, this is mod c square, and e to the power minus 2kx, right? 2kx dx is going to be 0, right? 2k mod x, right? And we can see this is mod x, right? So this is even function, so we can break the limit, right? So this is going to be 0 to 2 into 0 to infinite c square e to the power minus 2k mod x dx equal to 1. Okay, this is 1, right? Okay, well, so now we'll simplify it, right? So this is going to be mod c square into 2 is going to be 1 upon minus 2k e to the power 2kx 0 to infinity. Okay, so we'll put the value. So from here, value of mod c is going, value of c is going to be, this implies value of c is going to be, so if you do that, it's 2 will get cancelled, right? And this value is infinity, right? And this is going to be 0 is 1, right? This is minus, right? So we solve it, then this is going to be mod c square is going to be 2, sorry, k Okay, so value of c is going to be root k. Value of c is going to be root k. So now normalized wave function, complete wave function for the Dirac delta potential is going to be psi equal to root k e to the power minus k mod x. Okay, minus k mod x, root k e to the power minus k mod x. Okay, so this is the complete wave function, very important. Well, next point is this one. Now so here what we are going to do is we'll find out psi 1 and psi 2. Okay, for psi 1. So psi 1, so here if you find psi 1 at 0, okay, psi 1 at 0, so this is going to be put it right. So my psi 1 as 0, so psi 1 we know, right? Psi 1 is going to be, so psi 1 is going to be this, right? For region 1 at psi 1 is going to be root k. How? Because psi 1 we can see psi 1 is like this, root k e to the power minus e to the power kx. Okay, e to the power kx, and psi 2 is root k e to the power minus kx. Okay, so psi 1 at 0 it is going to be root k, and psi 2 at 0 it is going to be root k, right? So from here we can see at x equal to 0, okay, psi 0, psi 1 to 0 at x equal to 0, right? So this implies psi 1 0 equal to psi 2 at x equal to 0, both are equal, right? So it means this is psi 1, this is psi 2. Okay, yes, so it means this implies the wave function is continuous. Okay, is continuous at x equal to a. Okay, sorry, at x equal to 0, my apology, at x equal to 0, at x equal to 0. Okay, well, next point. Okay, next point is, this is very important point, guys. So now we'll check, we can see the first order derivative. First order derivative is discontinuous. Okay, second point is first order derivative. First order derivative is discontinuous. First order derivative is discontinuous. Okay, so this means we'll find out. Okay, so the first order derivative means this one, d upon d square upon dx square psi, sorry, my apologies. So this is first order derivative, right? First order means d psi upon dx, d psi 1 upon dx minus at x equal to 0, at x equal to 0 minus d psi 2 upon dx at x equal to 0. Okay, d psi 2 upon dx at x equal to 0. This value will find out, okay, because it's discontinuous. So that discontinuity we are going to find. Okay, d psi 1 upon dx at x equal to d psi 2 upon dx at x equal to 0 equal to, we'll find the value there, we'll put the value, right? So this is going to be d upon dx, psi 1 value will find right, and this is going to be d upon dx, and this is going to be this one, root k e to the power kx. Okay, at x equal to 0 minus, next is d upon dx root k, psi 2 value is e to the power minus kx, okay, at x equal to 0, at x equal to 0, okay. These are the value of psi 1 and psi 2, okay. So we'll differentiate it and then after differentiating, right, this is going to be root k and root k, so this one, right, root k, and this is going to be minus root k, okay, equal to this is this one, okay, after differentiating. So this value is going to be, that implies 2 root 2k, right, this one 2 root 2a, k is also there, guys, okay, because we will differentiate it, right. So k root k will remain same, k and e to the power iota kx minus e to the power minus iota kx, and when we put x equal to 0, e to the power 0 and e to the power 0, that value is going to be 1, right. So this value is going to be, this value is going to be 2 root 2k, okay. So this is the discontinuity, guys, okay, this much of discontinuity is there, okay. So first derivative is discontinuous. Now we'll solve it further, okay. So now we know the Schrodinger equation, okay. So that is d squared psi d squared psi upon dx square plus, we know, right, m h cut square and vx, right. So this is going to be v naught delta x, okay, upon h cut square, we know this value is v naught, right, minus v naught delta x, right, minus, and minus is going to be plus, okay. So plus v naught delta x is going to be 2m 2m upon h cut square 2m upon h cut square, and this value is going to be e, okay. That minus this is mod e, okay. This is the word, this is the value, okay. This one, this Schrodinger equation, after putting value e equal to minus mod e and v equal to v naught minus v naught delta x, we put the value, so we've got this equation, Schrodinger equation, okay. We can say, okay. So now we'll find out that this, for discontinuity, we'll differentiate, we'll integrate it and taking epsilon equal to 0, okay. So we have to find that discontinuity, okay. This is going to be limit epsilon tends to 0 here, right, limit epsilon tends to 0, and this is going to be minus epsilon to plus epsilon, will do it. This is going to be d squared psi upon dx square plus 2m v naught delta x upon h cut square, okay, psi dx, okay. Limit epsilon tends to 0, we have taken and integrated minus epsilon to plus epsilon, and right hand side is going to be 2m mod e, okay, 2m mod e upon h cut square h cut square, okay, h cut square, and this is going to be integration minus infinity to plus infinity psi, psi, which is function of x, right? Psi dx. Psi is function of x. Okay, now we'll simplify it. Okay, so this is going to be limit epsilon tends to 0, epsilon tends to 0. So we'll integrate it, right? This is double differentiation, right? So we write a d upon dx, d psi over dx we can write, right? And this is integration, this is differentiation. This will value give 1, so this is going to be d psi upon dx. Okay, d psi upon dx. Okay, and at epsilon equal to, at minus epsilon to plus epsilon, right? Similarly, this is going to be 2m v naught upon h cut square, and integration of this Dirac delta function and psi x. Okay, so that we know, right? If it is between this one, delta x equal to this, so Dirac delta function we know, right? Like this. I'll give example like delta x, integration delta x psi x. Okay, minus between this one, right? Delta x is delta x minus 0. So this is between 0. Yeah, 0 is between minus epsilon to plus epsilon, right? So this value is going to be psi 0, right? So in similar way we have solved it. So this value is going to be this is constant. So this is integration delta x psi x, right? So this is going to be, and the limit is between minus infinity to plus infinity, and we'll use Dirac delta property. So this is going to be psi naught. Okay, is going to be, this is for convenience you can write psi x, and this is psi x. Okay, this is the function of psi x dx. Okay, psi 0, and this function is going to be 0, guys. Okay, because psi value minus epsilon to plus epsilon, this value is going to give 0, because psi value we know, right? This is root k e to the power minus k mod x, right? So this value is 0. Now we'll see, we'll proceed further. Okay, so this is going to be this one. So this is going to be, we can write like this. Okay, because here epsilon tends to 0, right? So this is going to be psi d psi 2 upon dx at x equal to 0. Okay, this value at x equal to 0, or we can write first like this. This will be better. This is going to be limit epsilon tends to 0. So this is going to be d psi over dx at x equal to epsilon minus d psi over dx at x equal to minus epsilon. Okay, right? Then plus and this is going to be equal to minus 2m, will take this in right hand side, v naught psi naught upon h cut square. Okay, this one. So now we'll solve it further. So this is going to be this is going to be this one phi psi, right? Okay, psi equal to this one. Okay, so this is going to be now d psi upon d psi 2 upon dx at x equal to 0 minus d psi 1 upon dx at x equal to 0, because this limit is this one, right? Limit epsilon tends to infinity, right? So we can do that. Okay, so this is going to be equal to this one minus 2m v naught psi naught upon h cut square. Okay, so this is psi 2 and psi 1, right? And now we can write like this as well: psi 1 minus psi del psi 1 upon del x at x equal to 0 minus minus will get cancelled in this. If you do, you will take this and there and this one, right? So minus will take here. So this is going to be del psi 2 upon del x at x equal to 0. That is going to be plus 2m v naught psi naught upon h cut square. Okay, this one. Now this discontinuity we have already found, right? There is a discontinuity of this one, right? This one, this value 2 root 2k, right? So this is 2 root 2k is going to be 2m v naught psi naught upon h cut square, and value of psi naught we know, right? Because value of psi is this one, psi equal to root 2 e to the power minus k mod x, right? So now we'll put this is psi x. Okay, now that implies psi naught if you take x equal to 0, so this is going to be, this is root k, guys. Okay, root k, this is going to be k root k, and e to the power 0 is minus 1, so root k. So this psi naught value is root k. Okay, so now we'll put this into value of psi naught. So this is going to be 2 root 2k, 2 root 2k equal to 2m v naught, and psi naught value is root k. We have found here, right? So this is upon h cut square, right? So root k will get cancelled. Okay, 2 will get cancelled. So we'll square both sides, right? So this is going to be 2 root 2k. Just check. Here we have done some mistake. The mistake is the discontinuity, right? The discontinuity, this we have written wrong. This value is 2k root k, 2k root k. Okay, if we add it, okay, so k plus, right, 2k root k. Okay, so here this is 2k root k. Okay, now root k will get cancelled, and 2 will get cancelled. So value of k is m v naught upon h cut square. Okay, m v naught upon h cut square, m v naught upon, it's a very important, guys, value of k. Okay, you need to memorize it. Next, this one, this value is very important. So now we can easily find out this value of e is minus mod e, right? And since we know value of k is root 2me me upon 2me upon h cut square, right? 2me upon h cut square. Then this value, this is equal to m v naught upon h cut square. From here, this is going to be 2m upon h cut square. Will open the root and will square both sides. So m square v naught square upon h to the power 4. So this is going to be, value of e is going to be this one, m v naught square upon h cut square. Okay, m v naught square upon 2 h cut square. 2 is also there. Okay, this is the value of e. Okay, so now we can find, this is the value of e. Okay, so now we'll find out value of e. So therefore we know e equal to minus mod e, right? So this means e is going to be, this is the value of e for Dirac delta potential. The energy is going to be minus mod e. Mod e value is this, right? Minus m v naught square upon 2 h cut square. Okay, so this is the value of e, right? And for Dirac delta potential, the value of e is minus mod e, and mod e, the value of mod is same, right? So minus m v naught square upon 2 h cut square. Okay, 2 h cut square, very important. Okay, very important formula is this. So we can say single bound state possible corresponding to Dirac delta potential. Okay, that implies single bound state possible corresponding to Dirac delta potential. Okay, Dirac corresponding to Dirac delta potential. Well guys, so this is about the Dirac delta potential. Okay, and now we are going to solve some questions. Time is already over, but I'll complete those questions as well. Okay, so this is the one. Okay, so I'm going to solve some questions. Okay, question number 1 is related to Dirac delta potential. Okay, question 1 is very good question. Psi x is given. Okay, psi x is given a e to the power minus mod x upon a. Okay, this is the wave function given in 1D. This is in 1D. Okay, the potential corresponding to this wave function. Okay, the potential corresponding to this wave function, okay. The potential corresponding to this wave function. Okay, so psi x is given, right guys? This is a e to the power minus x upon a. Options are given. Let me write options first. Okay, very good question. Options are given, that is v equal to v naught minus v naught delta x. Okay, option B is given v equal to root k e to the power minus kx. Okay, option C is root k v equal to root k e to the power minus k mod x. Okay, right, so these are the options which is given. Okay, so since wave function psi is in the form a e to the power minus x upon a, right, and we know the standard form of uh, Dirac wave function for Dirac delta potential, right? So that is a e to the power minus k mod x, right? Here the value of k is from there. This we can say the value of k is given. K is minus k is 1 upon a given, right? K is 1 upon a. K is 1 upon a in this case. In this case, k is 1 upon a, right? K is 1 upon a. So we can write like psi equal to a e to the power minus 1 upon a mod x, right? So this is in this form, right? So we know if wave function is of this form, right, then then the potential is Dirac delta potential, and that is v equal to v naught delta x, right, minus v naught delta x, right? Simple, because constant can be anything, right? So it means this is Dirac delta potential, right? So which option is correct? This one, v equal to v naught minus v naught delta x. Okay, so this is very simple question and very important, right? So the standard form, this size is standard form of this, means this is Dirac delta, because this is the standard this is the wave function for Dirac delta potential, and this wave function is actually the wave function for Dirac delta potential. So that's why the potential is Dirac delta potential, and that the value is v equal to minus v naught delta x. Okay, next question. I hope you understood it, guys. Next question. Okay, time is already over, but I have to solve 2 more questions. Okay, I'm going to solve. Okay, next question. Question number 2. Very good questions these are. So find out the probability, the pro, the pro, find out the probability, of the particle being in bound state of Dirac delta potential, being bound state of Dirac delta potential. Okay, so find out the probability of the particle being in bound state of Dirac delta potential. So we need to find out the probability of the particle which is in Dirac delta potential, okay, which is in bound state of Dirac delta potential. Okay, and psi x is root k e to the power minus mod kx. Okay, this is the psi x, and psi dash x is this is the one, right? So we can write this is the psi x. Okay, or we can write, and we know the value of k, right? So k is, I have already, very important, I told you, k value of k is m naught v m m v naught, sorry, m v naught upon h cut square, m v naught upon h cut square. Okay, this is the value of k, value of k. Okay, h cut square. So Now what you need to do is you need to, so you can write value of psi x is, we have to find out the probability of finding particle in Dirac delta potential, bound state of Dirac delta potential, right? So this is going to be root m v naught upon h cut square, okay, e to the power minus k mod x, okay. So this is the psi x, and psi dash x is going to be similar to this root m v naught dash upon h cut square e to the power minus k mod x, okay. This is the psi dash x, okay. Well, so now we need to find out the probability, and we know probability formula, right? So this is mod square of expectation value of psi dash x psi x, okay. This we know. Now we'll put the value. So probability is going to be this one, integration minus infinity to plus infinity, okay, the value of this one, m v naught and m v naught dash upon h cut square, yeah, right. So this is going to be root m v naught dash upon h cut square e to the power minus m v naught dash mod x upon h cut square, okay. Here also we have put the value of k, guys, okay, value of k, here we have k, value of k, there, sorry, here, yeah, value of k, this side we have put it, okay. So this, and then this is going to be root m v naught upon h cut square to the power e to the power minus m v naught upon h cut square mod x, right. This is whole square, right. So this is just an integration. We need to solve very simple integration. So we'll take constant outside. So this is going to be and this is a even function, right. So we'll break the limit as well. So this is going to be 2m upon h cut, right. H cut square will take common because this will get integrated, right. This h cut root h cut square and root h cut square is going to be h cut square, okay. This one will take common, okay, and so this is going to be v naught dash v naught dash v naught root, okay. This is also going to be multiplied, okay. So this is the one, and then this will take outside, and this is going to be 0 to infinity. 2 we have taken, right, for breaking the limit. So it is going to be e to the power minus m naught m upon h cut v naught h cut square, and this is going to be v naught dash plus v naught dash plus v naught dash plus v naught x, right, dx whole square, okay. So we'll solve it further. So this is just an integration. You need to integrate it, okay. Very simple integration. So p is going to be this one, 2m upon h cut square root v naught dash p, okay, into e to the power minus m upon h cut square v naught v naught dash plus v, okay, x upon minus m upon h cut square v naught plus v naught dash, right, and we'll put the limit 0 to infinity whole square, okay, whole square. So we'll simplify it further. So this is going to be, this will get cancelled, so this is going to be 2 root p naught, and this value is going to be 0, okay, this one minus this 1, right, so this is going to be v naught v upon v naught plus v naught dash plus v naught dash whole square, okay. So value of p is going to be 4 v naught dash v upon v naught dash plus v naught, okay. So this is the probability, very important formula. So you can if you know this formula, so you can easily find out the probability of finding particle in Dirac delta potential, bound state of Dirac delta potential, right. So you don't need to write that calculation, you just need to note down this and memorize it, right. This is p equal to 4 v naught v upon v naught plus v naught dash plus v, okay. For example, I'll take one example, okay, like suppose now we know this formula, right, is 4 v naught dash v upon v naught dash plus v naught, right. This is the one whole square, right. This is the formula we know, okay. This is whole square, guys, okay. This is square, okay. So for example, if if v naught dash is given v by 2, v naught by 2, okay, in that case probability is going to be 4 into v naught by 2 into v naught, okay, v naught upon this one is going to be v naught dash plus v naught in place of v naught dash we'll write v naught by 2, right. So this is going to be v naught by 2 v naught whole square, okay, and we'll solve it, and this we are going to get 8 by 9, okay. So note down as a formula, okay, for Dirac delta potential, okay. So this is a very good question. Now next question we are going to do. Next question is question number 3rd. Okay, this is also a very good question. Okay. Okay, I'm going to complete this as well. So this is a particle is in question number 3rd. A particle is in infinite potential box, with boundary. Particle is in infinite potential box with boundary. With very good question, guys, and I'll tell you how to solve it so that you can solve it quickly, right. Best procedure I'll tell you, method, okay. Boundary, with boundary x equal to 0, and else this question is going to be very lengthy if you will do with typical method, okay. Then this question is going to be very lengthy, okay, and very lengthy integration you have to solve. But I'll tell you the best method by which you can solve this question easily and quickly, okay. So this is with boundary condition x equal to 0 and x equal to a, okay, has wave function psi x equal to 1 upon root 5a sine pi x upon a plus 2 upon root 5a sine 2 pi x upon a. Okay. Okay, so the wave function is this, has wave function this. Okay, the expectation value of energy. Okay, the expectation value of energy you need to find out. Okay, expectation value of energy. Well, so very good question. Okay, so you can see particle is in infinite potential box. Okay, boundary condition means this is particle is in infinite potential box like this. Okay, this is infinite potential box. This is infinite potential box. Okay, this boundary x equal to 0 and x equal to a means this is 0, this is a. Okay, so width is a. Okay, this is infinite potential box. Okay, so we need to find out expectation value. Okay, and wave function is given. So wave function which is given is psi equal to 1 upon root 5a sine pi x upon a plus 2 upon root 5a sine 2 pi x upon a. Okay, so we know for if particle is infinite potential box of width a, right, in that case we know the wave function is, for this wave function is, we know that is simple, that is root 2 upon a sine pi x upon a, right. So we have to convert this one with this form, right, so that we can easily find out this is the psi 1. Okay, and psi 2 is going to be root 2 upon a sine 2 pi x upon a, right. For 1D potential, the wave function psi 1 and psi 2 we know, right. This one I'm erasing it, but you know it. Okay, I've explained it. So we will convert this in this form so that we can write psi 1 psi 2. Okay, instead of this. So for that, what we can do this we can do is 1 upon root 5 a, we can multiply by root 2 upon a and divide by a upon root 2. Okay, so then there is no, this is not going to affect, right, the expression. So this is sine pi x upon a plus 2 root 5a into root a by 2 into root 2 upon a sine 2 pi x upon a. Okay, here we can do like this, a upon 2 and 2 upon a. Okay, so so this is going to be, then psi is going to be, right. So we can make, so this value we know, right, this is psi 1 wave function, this is psi 1 and this value is, this value is psi 1 and this value is psi 2, right, for the 1D potential box of width a, infinite potential box, right. This will calculate, a will get cancelled, so this is going to be 1 upon root 10, this we can write, this we can write psi 1. Okay, plus here again a will get cancelled and 2 is there, right, so 2 will get cancelled with root 2, right, root 2. So this is going to be root 2 upon 5 psi 2, because this value is psi 2, this value is psi 2. Okay, this we know, guys, right. So the wave function for, that is wave function for ground state and this is wave function for first excited state, right. So now it's very simple, psi we have got, but we need to normalize it. We don't know whether it's normalized or not, so we'll normalize it. Okay, For normalizing, what we are going to do, psi is going to be, so we will write a, will multiply by a root 10 psi 1 plus a root 2 upon 5 psi 2. We can write it, okay. Okay. So now we know how to normalize it, right? So for normal, so wave function must be normalized, right? So for normalization condition, we know normalization, right? How we'll do it? We'll do it like this, okay. So this is going to be this one. We'll square these coefficient and we'll make it equal to 1, okay. So this is going to be coefficient of psi 1 and psi 2. So a upon root 10 square plus whole square plus a square into root 2 upon 5 whole square is going to be equal to 1, okay. Right. So this will open it, so this is going to be a square upon 10 plus this is 2a square upon 5 equal to 1, right. This will be 4, guys. I think what mistake I have done, let me just check. Here. Right, so we can write here like this one, right, 2 upon root 10, okay. So this is 2 upon root 10, okay. So this is going to be this is going to be this one a into, right, so this whole square, so a square into 2 upon root 10 whole square equal to 1, right. So this is going to be so this is 4a square 2 square, right, 4a square equal 4a square upon 10 equal to 1. So from here this is going to be 5a square equal to mod a square, you can say, equal to 10, okay. So a mod a square is going to be 2, that implies value of a is root 2, okay. Value of a is root 2, okay. Now we'll put this value in equation 1, okay. So in place of a we'll write root 2. So this is then from equation 1 we'll put it. So the equation 1 is going to be this one, I equal to root 2 upon root 10 psi 1, this one, right, yeah, and plus second is going to be 4 upon 5, or we'll write it like 2 upon 10, two root 2 upon 10, okay, because this is 2 is there, a is 2 root 2 upon 10 psi 2, okay. So we will simplify it. So this is going to be psi is going to be 1 upon root 5 psi 1 plus this is going to be this is root 10, guys. Okay, 10. So this is going to be 2 upon root 5 psi 2. Okay. Now we'll find out the energy and the expectation value we know, right? E equal to P1 E1 plus P2 E2. P1 is coefficient whole 1 upon 5 whole square, C1 square, right? This is coefficient C1 and this is P2 is C2 whole square, right? So E1 energy for first excited state, we know. Energy for second excited state, we know, right? E2. So this is going to be 1 upon 5. Energy of first excited state is pi h cut square for 1 day. The particle is infinite square well potential, pi square 2 ma square, right? Plus this is going to be 4 by 5 the C1 whole square, right? P2 is P1 is C1 mod square, right? C1 is this, that is 1 upon 5. P2 is C2 mod square, that is this one, 2 upon root 5, that is 4 upon 5. Okay. So here energy for first excited state, energy we know. The particle is infinite one-dimensional box of width A, and this is 4 by 5 into E2 value. E2 value is we know, that is 4, 2 to the 4, right? 4 pi square h cut square upon 2 ma square, right? So this is going to be, so we can take pi square h cut square upon 2 ma square common, right? Okay, so this is like 1 upon 5 plus 16 upon 5, right? Because pi square h cut square upon 2 ma square we have taken common. So energy expectation value is going to be pi h cut square 2 ma square, and this is this we added, right? So this is 17 upon 5, 17 upon 5. So this is going to be 17 pi square h cut square, okay, 17 pi square h cut square upon, this is 5, right? Okay, 10 ma square, 10 ma square, 17 pi square h cut square upon 10 ma square. This is the expectation value, right? So this is the procedure, guys. Else if you have given this normalized function, right, and you, so if you want to take the if you want to calculate this wave function, okay, then you will do psi star integration psi star psi minus infinity to plus infinity upon psi integration minus infinity to plus infinity psi, right? So this is going to be very lengthy, and so this is the best procedure by which you can easily solve it. Okay, guys. Well, so today we have studied first rectangular potential barrier, okay, and then we rectangular potential barrier, and then we studied Dirac potential, and we solved questions related to them. Okay. So okay. Well, guys, before ending the class, I would like to request everyone who haven't subscribed my channel yet, please subscribe my channel and watch my lectures, which are absolutely free of charges and are going to help you to crack the exams related to physical science. Okay, guys. So it is almost 2-hour class today. Okay. Okay, guys. Bye now.